Let's talk about the net change theorem. So the net change theorem looks a couple of different ways. Let's take a look at this framing of it. A new value of a changing quantity equals the initial value plus the integral of the rate of change. So I can write this in a couple of different ways. The first way that I could write it is I could write it using the fundamental theorem of calculus, part 2. So from the fundamental theorem of calculus, part 2, we know that the integral from a to b of f prime of x dx, that's going to be equal to f of b minus f of a. So this quantity that I've just written here, this is what we mean by net change. Okay, so the net change is basically just the area under the rate of change curve. Now, what I can do with this formula is I can basically manipulate it so that I could solve for f of b. And f of b is basically going to equal to f of a plus this integral from a to b of f prime of x dx. Okay, so different books express the net change theorem in different ways. Some books do it in the way I've written here in blue. Other books, they solve for the f of b and they say, oh, if you just started at f of a and then you added the integral, this integral is the net change, and then you end up at f of b. Why don't we look at an example together and we could make sense of all of this. So in example 4, it says, given a velocity function v of t equal to 3t minus 5, this velocity is measured in meters per second for some particle in motion from the time t is equal to 0 to the time t equal to 3. Find the net displacement of this particle. So according to the theorem, all we need to do to find the net displacement is integrate our velocity function, which is a rate of change. So that velocity function is 3t minus 5 dt, and we want to integrate that from 0 to 3. Okay, so we're going to use the fundamental theorem of calculus part 2. The antiderivative of 3t is 3t squared over 2, and the antiderivative of negative 5 is negative 5t, and we're going to evaluate that from 0 to 3. So when we substitute in, we're going to get 3 squared is 9, 9 times 3 is 27, so we get 27 over 2, minus 3 times 5 is 15. That's the first term, and when we substitute in 0, we're going to get 0 minus 0. So when we simplify all of this, we're going to get negative 3 over 2 meters. And let me highlight that answer right here. Okay. I want to emphasize one final thing, which is this 3t minus 5, the velocity is the rate of change of the position function. So to be perfectly clear, when we're saying net displacement, this net displacement means the net change of the position. Okay. When we work with net change, we also call the net change net displacement. So I probably should have mentioned that before we even started this example. Um, let's take a look at what we mean when we say total distance traveled now. Total distance traveled and net displacement are two separate things. Net displacement is basically the difference between your starting point and your ending point, whereas total distance traveled sort of tracks going forwards and going backwards, or going up and going down. So we've actually seen this before. The net distance traveled is going to be the integral from a to b of the absolute value of the velocity function with respect to t. Okay, so when we saw it in the past, we looked at it in terms of area. In other words, net change was the net area and total distance traveled was the total area. And now we're just applying it in the special case where the function we're working with is the velocity function. Let's take a look at example 5. Example 5 is going to be a good example for us to look at this. So we're given a velocity function, v of t equal to 3t minus 5, again measured in meters per second. And we're going from t equal to 0 to t equal to 3. But this time we want to find the total distance traveled by that particle. So the first thing that we should do is we should figure out where this velocity function is equal to 0. So we're going to set the velocity function v of t equal to 0. And that means we're going to set 3t minus 5 equal to 0. And solving for t, we're going to get t is equal to 5 over 3 seconds. Now, our total distance traveled is going to be equal to the integral from 0 to 3 absolute value of 3t minus 5 dt. And what I want to do is I want to basically rewrite this 3t minus 5 in absolute value function as follows. This is going to be 3t minus 5 if t is greater than 5 over 3, and it's going to be negative 3t minus 5 if t is less than 5 over 3. And remember, the reason I know that is because I found the point where it crosses the x-axis. And if you plugged a test point in for t, like t equal to 3, then we could see that, we're going to get a positive number. Whereas if you plug in a test point like a 1 inside here, you're going to get a negative number. Okay. Now that we have broken down what our absolute value function looks like, we can use our property for definite integrals and split this integral up into the integral from 0 to 5 over 3 plus the integral from 5 over 3 to 3. And for the values where this inside part is positive, in other words, where our t is greater than 5 over 3, we're just going to write 3t minus 5 dt. And the parts where the inside here is negative, in other words, from 0 to 5 over 3, we are going to write negative 3t minus 5 dt, like so. All right. So now we're going to calculate the antiderivative of each piece. If you'll let me, I am going to distribute that negative. So maybe I'll write an extra line here. So this will be the integral from 0 to 5 over 3. This will be negative 3t plus 5 dt. And for this second integral, I can find the antiderivative immediately. That antiderivative is going to be 3t squared over 2 minus 5t, going from 5 over 3 to 3. Okay, so let's find the antiderivative of that first integral. That's going to be negative 3t squared over 2 plus 5t evaluated from 0 to 5 over 3. All right, so now I can substitute my values in. So we're going to have 3 times 3 squared over 2 minus 5 times 3. Let's put that in parentheses, minus 3 over 2 times 5 over 3 squared minus 5 times 5 over 3. Okay, so let me move this a little bit more. I still have to simplify that first piece over here. So for this first piece, we're going to have negative 3 over 2 times 5 over 3 squared plus 5 times 5 over 3. And when you substituted this 0, you're going to get a 0 coming out. So when I simplify this whole thing, I'm going to end up with a single number. And that number that I get when I simplify this whole piece is 41 over 6. And I already forgot our units. Let me just check here. Our units are in meters per second. So this will be meters. Okay, so I'm going to highlight that. And that's it, folks. So we will look at some examples and more examples in class together. Take care.